Hello everyone, I am going to explain the benzene and its derivative, that is the structure of benzene that is discovered by Kekulé. So today briefly I am going to explain the Kekulé structure for benzene. Benzene was known to have the molecular formula C6H6, but its structural formula was unknown. If benzene was a straight chain unsaturated hydrocarbon, that is carbon carbon single bond or carbon carbon double bond or carbon carbon triple bond character is there, that is known as your unsaturated compound. So if the benzene was a straight chain unsaturated hydrocarbon, it should readily undergo addition reaction just like other alkene or alkyne. For example, bromine should add across the double or triple bond as shown below. This is the reaction, possible straight chain structure addition reaction. When this triple bond character compound or alkyne, when it react with Br2, it will give double bond character compound or maybe double bond and triple bond character compounds. But when bromine is added to benzene at 25 degrees centigrade and 1 atmospheric pressure, no reaction seems to occur. So the possible structures for benzene involving double and or triple bond arranged in a chain seemed most unlikely, as this should undergo the addition reactions. If bromine is added to benzene in the presence of FeBr3, it undergoes a substitution reaction in which one of the hydrogen atoms is replaced by a bromine atom to produce a compound with the formula C6H5Br as shown as below. That is C6H6, when treated with bromine in presence of FeBr3, it will give C6H5Br plus HBr. In this respect, benzene was behaving much more like a saturated hydrocarbon, only single bond between carbon atoms. So, the first structure proposed by Kekulé for benzene in 1865 did not contain any double bond but did arrange the 6 carbon atom in a ring as shown as below. This is the structure, this below structure. So this is the first structure discovered by Kekulé. Then Kekulé realized that this molecule breaks the tetravalence rule for carbon. That is, each carbon atom is forming only 3 bonds rather than 4. So in 1872, Kekulé proposed a benzene structure composed of 3 alternative single and double bond as shown the figure. This is the structure according to the Kekulé. Please note that although the carbon atoms are not retained within the structure, it is always understood that a carbon atom exists where 2 lines of the hexagon join, so that there are 6 joins, 6 angles, and therefore 6 carbon atoms. In this structure, each carbon atom is bonded to a hydrogen atom and to 2 other carbon atoms. One of the carbon-carbon bonds is a single bond. The other carbon-carbon bond is a double bond. Each carbon atom has made 4 bonds. While this structure does not explain why benzene does not undergo addition reaction, it could explain why benzene forms only one structural isomer when benzene reacts with bromine in a substitution reaction as shown below. So the first one, the proposed benzene structure. This proposed benzene structure, when treated with bromine, it will give only one structural isomer, that is 1 bromobenzene plus HBr. His idea was that these were in a rapid equilibrium, so rapid that there was never a fixed location for the double bond. One could say that an approaching bromine molecule could not find a double bond to react with. The other proposed ring structure for benzene would have predicted more than one structural isomer for the product of the substitution reaction as below. Here only one thing is there, isomer. What do you mean by isomer? So isomer means same molecular formula but structurally they are different from each other. So in that reaction, the first one, the proposed ring structure of Kekulé, when treated with bromine, it will give two isomeric form. Structural isomer 1 plus structural isomer 2. So bromine may be attached at position number 1 in case of structural 1, or maybe structure 2, bromine may be attacked at position number 2. This is the hypothetically we can understood, that is position of bromine atom only. What would happen if another hydrogen atom were replaced or substituted with a bromine atom? So monobromobenzene, that is C6H5Br, when treated with bromine Br2 in presence of FeBr3, then another one hydrogen atom also replaced by bromine atom, and it will give C6H4Br2 plus HBr. So now you see how many structural isomers of C6H4Br2 would be produced. When monobromobenzene treated with bromine in presence of Br3, it will give one isomeric form, that is the structural isomer 1, that is 1,2-dibromo, or structural isomer 2, that is 1,3-dibromo, or structural isomer 3, that is 1,4-dibromo, or maybe structural isomer 5, 1,3-dibromobenzene. Structural isomers 1 and 4 are different because in isomer 1, the two bromine atoms are bonded to the carbon atoms on a carbon-carbon bond, while in the isomer 4, the two bromine atoms are bonded to the carbon atoms on carbon-carbon double bond. However, when the C6H5Br made from benzene reacts with bromine in a substitution reaction, only 3 structural isomers of C6H4Br2 are produced. In order to resolve this problem, Kekulé proposed that the benzene ring is in a rapid equilibrium between structures in which the double bonds are in the alternative positions as shown in the structure 1, structure 2, structure 1 containing the double bond, structure 2 also containing double bond. They are having that alternative single bond and double bond. So When bromine react with C6H5Br, that is monobromobenzene, in a substitution reaction to produce dibromobenzene, that is C6H4Br2. Pairs of structural isomers of C6H4Br2 are in equilibrium with each other. This means that structural isomers 1 and 4 shown above, which only differ in the that Br atom are bonded across a single bond or a double bond, are now in a rapid equilibrium with each other as shown in that following structure. So bromine atoms are adjunct carbon atom. Structural isomer is isomer 1 has bromine atom across carbon-carbon single bond structural isomer. 4 has Br atom across C double bond C. According to the Kekulé, these two structural isomers of C6H4Br2 are in such a rapid equilibrium that they cannot be separated out as two separate molecules. So it appears that there are only three isomers instead of four. Thank you.